Now, if I ask you a question, that is, how do you want to study any particular topic, or let's say, how do you want to know about an organism which you have never heard of, never seen, and that's right in front of you. There's an organism right in front of you. You want to study about that organism. What are the different characteristics and traits on those organisms? The only way to study is give a stimuli and observe the response given by it. Based on that, based on the response which you get, you will end up getting a picture or characteristic picture of that organism. We have the same situation when we want to study about atom. Now, as we know, atoms are quite small, so the only way to give a stimuli is through light. Now, right now, for the past few videos, I have been learning about light. What is light? What are the different theories corresponding to the light? Now, as we are done past that, our main intention is to find out what exactly is the structure of atom. So, in this particular video, we will be learning about famous theories about atoms. So, first up is Plum-Pudding and Rutherford's model. So, let's find out what are those two models. Now let's shift our attention to the different atomic theories, or let's say theories or ideas concerning the structure of atom and what were the constituents of the atom and how they were arranged inside the atom. So we will discuss different theories given by different pioneers in the field of physics, that is Rutherford, J.J. Thomson, Bohr. We are discussing the theories, three theories given by these three fellows. Why only these theories? Because they were closest to the reality. That is, we still don't know the exact structure or the exact outlook of atom, but the experiments or the results which we got is closest to the reality. Or let's say theories, according to these three theories, their predictions, they are very close to the reality, that is the experimental results which we get. So let's start off with Plum-Pudding model, one of the earliest model given by J.J. Thomson. So before I actually start speaking anything about Plum-Pudding, let's just know let's say a few facts about Joseph John Thomson, that is J.J. Thomson. So here's a typical English lad. Was born and brought up in Manchester. He stayed there. And he was majorly known for mentoring great scientists. He in itself was also a very great scientist. He won Nobel Prize. As you can see, he won the Nobel Prize around 1906, right? And 8 of his fellows got Nobel Prize. That is, 7 of his research assistant and his own son won the Nobel Prize. So he was very influential. He was a good motivator and a great scientist indeed. So now that you know a few facts about J.J. Thomson, now we can actually study Plum-Pudding model. So as the name suggests, Plum-Pudding model, it's basically the idea is derived from a typical English Christmas pudding. So the idea or the inspiration which J.J. Thomson got about the structure of atom was from Christmas pudding. So now in many books, in many materials, you will find a watermelon analogy is also given. The reason being, the English Christmas pudding is kind of a rare thing in many countries, especially in Indian subcontinent. It's kind of rare. So though we actually come up with a Plum-Pudding model, but we bring in the watermelon analogy such that everyone gets the picture what is exactly the model or what J.J. Thomson was trying to say. So what J.J. Thomson said that in a typical pudding you have some plums, right? There are some spaces. Now consider the total pudding to be positively charged and the plums to be negatively charged, and that's how an atom is. So your atom is basically a big bowl or a big ball where the mass, charge, everything is uniformly distributed. The positive charge is uniformly distributed, and there are discrete spaces where the negative charges are. Just like in the case of watermelon, where I can see that negatively charged can be thought to be seeds, whereas the edible red portion of watermelon is positively charged. So that's the model which, plum pudding model which J.J. Thomson came up with. So here are the few facts of how he came to know, or how he got inspired regarding this model. That is, he thought the currants or the dry fruits which are there, which are sprinkled or which are there in the pudding, in typical English pudding, he considered those currants or the dry fruits in a pudding to be negatively charged, and the rest of the pudding to be positively charged. And he sort of exported this idea to an atomic scale. That is, okay, atoms are also like pudding, where it's there are some objects that are negatively charged, there are some objects that are positively charged. And as I told you, watermelon analogy is thrown in now and then because of unfamiliarity with the concept of pudding in different countries and different languages. So that's your plum pudding model. Now, what were the drawbacks of plum pudding model? See, Thomson attributed that the mass of atom is distributed throughout the atom, or the total atom is the total mass is distributed throughout the volume of an atom, which in fact is not true. Why? It's because of the direct observation from Rutherford's experiment of gold foil. We'll discuss what was the experiment of Rutherford, but please keep in mind that the crux of the model, the heart of the model, that is, it's solid, everything is distributed, there are no spaces, there are no gaps, or there are no voids. It was shattered by the Rutherford's observation. Okay, so, and a fun fact, Rutherford actually came up with his the idea of carrying out an experiment solely to prove J.J. Thomson wrong. His main idea is, J.J. Thomson came up with the model. He was his contemporary, so he decided, okay, I need to come up with an experiment which will prove this guy is wrong. So he designed an experiment and put his theory to the test and proved to the world that J.J. Thomson was wrong. That was his intention. That was the Rutherford's intention. So we'll discuss what exactly did Rutherford do when we will discuss Rutherford's model.
Now let's have a look at plum pudding model, that is the model suggested by Thomson. Now what he suggested, as we have discussed in the earlier slides, that there is a sort of shape like this, and there are dots like this. And what is this shape and dots? Is basically these dots, they are electrons, and this suspended uniformly distributed mass is the positive charges denoted by protons, which are distributed throughout this particular red area. Now this model is, as you know, it's a plum pudding model. Now we will sort of eject or throw out particles at it. So I have throwing out particles, that is, these are the alpha particles, and energy of the alpha particles are like this. That is, I have decreased it to the minimum energy, so they are moving very slowly. And the scale of the atom, which Thomson predicted, was around 300 picometer. So this is the whole, let's say, the distribution of the whole atom was only 300 picometer, which we came to know is not the correct version of it. So according to the theory, so what I'm trying to do is what he said. I've simply constructed it through the simulation, through this particular software, that this is what Thomson said, and I'm performing an experiment, that is throwing out alpha particles at it. So I'm increasing the energy of the alpha particles, and I can also use this beautiful property of showing the traces. So I use the traces, that is, I know what's the part of each alpha particle. So again, if I increase the energy, I can see they are moving faster. So what I observe is that they're barely getting deflected or moved away. So this is purely according to the model. This is not a reality, to be frank, because we know that the atom doesn't exist like this. So according to the plum pudding model suggested by Thomson, this should have been the observation when an atom is facing a bombardment of alpha particles from one particular end. This should have been in, let's say, the observation, which we came to know is not the correct version of it, because there will be some alpha particles which will be deflected, which will be thrown back completely. So there are only very few of it. There is none of them. They are actually getting deviated that much. Or let's say all of them are moving in a straight line.
Okay, now let's start off with Rutherford's model. What Rutherford's idea of atom was. This is purely accidental in nature. Rutherford, he didn't have any intention whatsoever to come up with an atomic theory. What he did is, J.J. Thomson came up with a theory, so his main intention was to disapprove that guy. So he designed an experiment. Disapproved J.J. Thomson, but while doing so, he got few observations, and the other observation clubbed with the original observation, it was so beautiful, it was so beautifying. The whole structure of atom was, you can literally visualize the structure of atom based on his observation. It was so beautiful. So he therefore came up with a model. That his observation was so clear, they were so expressive that you can literally come up with a theory. So he did that. So the Rutherford model was purely accidental in nature. Now, a few facts about this Rutherford guy. Rutherford was from New Zealand. He moved to Europe, or let's say England to be precise, to carry out his further study. He lived there and won a Nobel Prize. That's his life story in a nutshell. And a famous quote, which I guess most of you guys know about this, is all science is either physics or stamp collection. That was Rutherford's take on any subject in science. So he was known for, like this typical remark or quotations or one-liners. So he was kind of expressive, and that too in a good way. So now that we have known few facts about Rutherford, and you can dig in some more at your own time. Now we should move on to the Rutherford's model. Now, this was the setup which Rutherford started with. So what he did is, he had a source of alpha particles, so he's going to throw some alpha particles at a very, very, very thin foil. You cannot imagine how thin it is. It's few atoms thick, hundreds of atoms thick, that's it. Like 200, 300 atoms thick, that's it. That's how thin this foil was. And it was surrounded completely by circular fluorescent screen. That is, I have some illuminating screen. That is, if there is some sort of collision of any particle with the screen, there will be illumination, or there will be bright spot on that particular screen. So he surrounded the complete setup with the screen. What he did is, he bombarded the thin foil with alpha particles, and obviously, as you expected, there will be scattering. Now, and the scattering, at what point or at what angle did the particles or alpha particles deviated, we can easily find out, because we know at what spot they actually hit the screen. So I can easily find out how much scattering took place and by how much amount it took place. So right now I'm just waiting for the results. So let's move on to the results and what they actually convey. Now, Rutherford's experiment was done, observations and its implications are noted down over here. So most of the space inside the atom is empty. Now this was alarming. Because alpha particle passed through the gold foil without getting deflected. What actually happened is, I designed this experiment. Let's say I am Rutherford, I designed this experiment. I have a gold foil in front of me. Thin gold foil in front of me. I can literally see there is a gold foil, and I cannot see, on the other side of the gold foil because it's opaque. What I'm expecting is, I'm throwing a stream of particles at gold foil. I'm expecting to reflect back or move in this direction or that direction. I expect very less gold particles to actually make their way to the other side of the gold foil. What actually happened is, almost all the alpha particles, they moved as if there was nothing in their way. nothing on their way. They simply move past their goal for it. 200, 300 atoms, simply they move past through it, as if nothing was there on their way. Now, this was alarming, given that atoms, according to the previous model of J.J. Thomson, were solid. That is, the total atom and mass and everything is uniformly distributed. So you can't penetrate through that, obviously. Now, due to this observation, it clearly stated that most of the space in an atom is empty, completely empty. Now, next observation is very few particles were deflected from their path. Okay, very few particles were deflected from the path, indicating that the positive charge of the atom occupies very little space. As there were small amount of deviation, only few particles were deviated, it means there is some positive charge. And the fact is, only few alpha particles were deviated. It means only few alpha particles actually were able to move close to the positive charge, the location where the positive charge is kept inside the atom. Only few alpha particles were able to move nearby it. So it means that the positive charge is located at a very confined space, at a very little space. Third observation, a very small fraction of alpha particles were deflected by 180 degrees. So it means the alpha particles moved, they came back on the same way they were. This proved that the spot where the total positive charge is also the spot where the total mass is concentrated. So the total mass, let's say almost all the mass is concentrated on the center of the atom, and that is called as nucleus. So these are the observation I came up with. These were the observation which we witnessed, and the implication or let's say the conclusions were drawn correspondingly. So you can literally visualize that the atom is hollow, this big hollow. At the center there is a small space where the nucleus, which is called nucleus, and I have protons and neutrons over there, and obviously electrons are moving outside. That's how an atom looks like. So you can literally visualize inside your head how, according to Rutherford's conclusion of his observations, how an atom looks like. Now, this is the observation given in a few pictures. Again, the same stuff is being repeated over here. That is, that atom consists of positively charged nucleus, which is surrounded by electrons moving around it. Electrons and nucleus are held together by Coulombic force of attraction. The size of nucleus is very small as compared to the size of atom. Right? Again, this was properly explained when we were discussing the previous slide. What were the drawbacks of this model? Now, what happens is when an electron or when a particle is moving in a circle, it is undergoing acceleration. There is acceleration associated with that particle. Now, what happens when a charged particle is accelerated? It radiates out energy in the form of electromagnetic waves. So, if I have an electron moving around moving about a nucleus, it's undergoing acceleration first. Second, it means it will be radiating out energy. Now, if that particular particle is radiating out energy, it means it's losing energy and it will simply spiral down to the nucleus. We know that that's not happening, so it means there's something more to it. So that was the drawback of, or one of the biggest drawback of Rutherford's model. The other drawback is Rutherford didn't say anything about electrons. He just said the electrons are moving at a very, let's say it's a considerable distance away from a nucleus. He just said that. And he didn't say that whether two electrons are moving together, 7, 10, 12, how many electrons are moving together or how are they arranged. He didn't say about that. He only focused his attention to comment about nucleus. So, according to Rutherford model, we know everything about nucleus, but we don't know anything else about the atom.
So now let's have a look at the Rutherford model. So this is a simulation. Now that we have studied about the Plum-Pudding model and also studied about this simulation or visual aspect of Plum-Pudding model. Now we'll look around for Rutherford's model. Now you can see that this is an atom placed over here, and these are the orbit of the innermost electron. You see this electron passing over here. Now it will come out like this over here. Just have a look at it. The electron coming out over here. This is an orbit. So again the electron will go over here, then will come back over here again. Why I have actually neglected the electrons movement over here? Because I am bothered by Rutherford's model. So Rutherford's model was primarily giving us a very good set of information about the nucleus. So that's why I've set the scale to be 150 FM, because I want to know only about the nucleus. So again I will start off with the bombardment of alpha particles. So the alpha particles will start to move. So you can see that few of them we are actually moving around this region. They are deflected back, or many of them they are actually thrown completely back. That is total reversal of their path. So this will have more good amount of visual aspect if I actually introduce the path tracer over here. So once I introduce the path tracer, you can literally figure out how heavy or how powerful is this central nucleus of an atom. So this nucleus is actually positive charge and is also deviating the positive charges in different parts of their own. So this is what Rutherford actually suggested, and this is what we actually observed. So he, based on his experiment, he gave his version. So corresponding to his observation, this model has been designed in front of you. Whereas Thomson came up with his idea without any backing whatsoever from experimental point of view. Whereas Rutherford performed an experiment based on the observation which he got. He came up with his version of atomic structure. So this is how an atom will behave, or nucleus will behave, when we bombard alpha particles at it.
Now that I have gone through two of the most famous theories about atoms, one being Plum-Pudding model and Rutherford's model, it actually gives me few flaws but few great observation about the rough structure of atom. Now that I know the rough structure of atom, I want to apply finer details to this, such that this theory or my idea about the structure of the atom as a whole stands correct or stands 100% pure. So right now my main intention will be applying those fine touches to the rough setup. So what are those fine setups, or the touch-ups? Let's see in the next video.